Okay, here we go. All right. Okay. Let me move this over a little bit. I think that'll be a little better. Okay, can you guys see that? Okay, do you want me to turn the lights off again? Turn those lights off. Turn those lights on. Okay. All right, and then let me increase the exposure a little bit. Okay. Okay, I think that'll work. Okay, so I think we had just introduced the Joule-Thomson coefficient last time. Is that right? You got something like this. And of course, this term right here is the heat capacity. So we can rewrite this as negative Cp like that, right? And okay, so one thing that I wanted to go back and just point out, we kind of went through a derivation of this relationship that kind of took us through we had to write out the full differential for H, and then we had to do a little bit of fuzzy math. But if you notice, this right here is just the cyclic rule. Okay, so if I take these three variables right here, H, P, and T, I can write it out like this. And then I'm just going to move these around. So I'll go oops, that's a T. So that equals -1, right? So this is just the cyclic rule. And if you take these two partial derivatives here, you can move them to the other side of the equation by multiplying by their inverses. And notice these are just the inverses of those, right? This and that are inverses. And then this and that are inverses. So there's sort of a back door to get here, which is the cyclic rule. Okay, but what we were after is this: how enthalpy changes with pressure. And of these terms, this one here, partial of T with respect to P at constant H. This is sometimes abbreviated as mu subscript JT. This is the Joule-Thomson coefficient. Okay, that's the Joule-Thomson coefficient. And the thing that we were really interested in it does not have a letter, but this is just called the isothermal Joule-Thomson coefficient. Okay. So the isothermal Joule-Thomson coefficient tells you how enthalpy changes with pressure at constant temperature. This other term here, the mu subscript JT, is called the Joule-Thomson coefficient because, like we mentioned in the experiment, this is actually how it's experimentally determined because we had the gas that got pushed through the porous plug, and then we had some initial set of conditions and some final set of conditions, and it turned out that was an isenthalpic process, meaning enthalpy didn't change. And so that's how it's measured. Enthalpy doesn't change, and I measure the pressure and the temperature for those. So if you're wanting to know how enthalpy changes with pressure, now that we have this Joule-Thomson coefficient, we can write out this, which is what we want. This would be at constant temperature, right? So there's no temperature term over here. And this is equal to negative Cp mu subscript JT dP. Or, if I want to write this out in integrated form, delta H is the integral of Cp mu JT dP. So this tells us how enthalpy changes with pressure. Now, if you have a variable temperature as well, then there's another term that shows up. So if you have variable temperature, then you've got this term also. This would account for the temperature variation. You'd integrate over the temperature as well. And so you can calculate the enthalpy change for a process that has both variable temperature and variable pressure. Now typically, and you guys have a little bit of you have a little bit of experience with this. We use tabulated enthalpies instead. You guys remember using tabulated stuff in engineering thermodynamics? Yeah. So you have the table, and it tells you the enthalpies for like water at all these different temperatures and pressures and stuff. And then you just go look it up, right? Well, how are those tables generated? Oh, they generate them by, calculating the enthalpies for all those. I mean, those are not all experimentally measured. They're not going through and saying, okay, well, let's find out what the enthalpy is at this temperature and this pressure so we can put a number in the table. Those are all calculated. Okay, so I want to talk a little bit about let's see. In your homework, have you guys looked at your homework yet? You printed it off. So in your homework, I think there's some partial derivative stuff. I want to work an example problem using of partial derivatives, just to show you how this stuff works. But you've got a heat capacity or Joule-Thomson coefficient question in your homework, so you need to take a look at that so you can see if you've got questions about it. Okay, so I want to work a problem out of your textbook. This is problem 22-12. And it's looking for this partial derivative here. And we're wanting to show that this equals this. So this is how internal energy changes with volume. Okay, so how do you solve a problem like this? You have to, the first time you do something like this, it's not always obvious where to start. But we're going to start with A equals U minus TS. So in your partial derivatives homework, you've looked at that too? Did you print both of the homework sets off?
I did the partial derivative.
You did the partial derivative one. Okay, yeah. So the partial derivative one, okay, so this will be helpful. Now we're looking for this partial derivative right here, partial of U with respect to V at constant temperature. So what we're going to do is take the derivative of this equation with respect to volume, holding temperature constant. Does that make sense? Yeah? Okay. So the left side of the equation is what? A prime, well, we'd actually write it out like this. Partial of A with respect to V at constant T. All right? Okay, and then what about the right side of the equation? Partial of U with respect to V at constant T. Yeah, del U, I guess. I don't know. I'm not a mathematician, so. And then minus, okay, what about this term right here? Do I have to worry about the product rule? Because this is a product, right? It's T times S.
But since T is being held constant,
It's constant, so what do you do with constants? You pull it out. So we can pull it out, and then we're left with that. So this is the partial derivative we're interested in, which is how internal energy changes with volume at constant temperature. Okay. And we're trying to show this right here. Let's just go ahead and rearrange it so that we can get stuff. We're going to just move this over here and rewrite it as, not H, partial of U with respect to V at constant T equals partial of A with respect to V at constant T plus T partial of S with respect to V at constant T. There we go. One step closer. All right, so at this point, if we look, we'll notice that I've got this T times something. T times partial of S with respect to V at constant T. Up here, I have T times something. It's the partial of P with respect to T at constant V. So how can we make that substitution? And then I also have this partial of A with respect to V at constant T, and then I have this P term. Well, what is the differential of A in terms of its natural variables? It's this. Now, if I write it out, so what are its natural variables? P and S, those are not its natural variables. Volume and temperature. Remember, these are the independent variables, V and T. It's the thing that you integrate over. Everything else is a dependent variable. So pressure is a dependent variable. Entropy is a dependent variable, right? These are your two independent variables. So I could write out the differential of A in terms of its natural variables, just like this. Right? This is just writing it out just like we've done before. Now, what do you notice about the partial of A with respect to V at constant temperature? What must that be equal to? Looking at this guy right here. It would not be 1. Wouldn't be 0. It would be negative P. Yeah. Those terms have to equal each other. Because I have here dA equals something dV plus something else dt. Well, here I've got dA equals something dV plus something else dt. So the somethings have to be equal, and the something else's have to also be equal. Right? So notice that we can just substitute in negative P directly into this equation. So our equation now reads this. We're close now. We've got negative P, a T, and then something else, but I want it to look like this. So let's go back down here. What kind of relationship might help me if I'm trying to go, from here to there? A Maxwell relation, that's right. A Maxwell relation. Okay, so what's the Maxwell relation for dA? What? That's exactly what I need, isn't it? Because then we can take this. Oops, it's right here. I almost went up too far. And it goes right in there. Make that substitution. And then I get the top equation, which is what we were after. So in some of your partial derivatives homework, this is kind of what you have to do. I don't think you have anything. If it's this complicated, I think it gives you some steps. It's like start here, and do that kind of stuff. But But this is the kind of thing that you want to do. So you want to, this is one of the key parts where you write out the full differential in terms of its natural variables. And then you can make these kinds of comparisons. Okay. All right, do you guys remember heating curves? You don't remember heating curves? A little bit? Something that looks like this? Sometimes it's put Q on the y-axis, but we're going to go with H. And it looks something like this. Remember that? So if we're just going through a single phase transition, like this could be like, water, liquid water. This is vaporization, and then this is the gas, water, right? And then we said, okay, well, the way that you solve these problems is that you have delta H equals in CP delta T, right? And then you've got this one is delta H equals in delta H vaporization. And then up here you've got delta H equals in CP delta T, where this is all for the gas, right? So you'd have the heat capacity for the gas, the temperature change for the gas, and all that stuff, right? Now, does all that seem kind of disjointed, though, right? You're like, okay, well, I got to do this, and then that, and then that. Well, it turns out that enthalpy changes, this is all just one big, massive equation. So enthalpy changes, you can boil them down when more than one substance or phase is involved. Then you've got an equation that looks kind of like this. All right, now this is for two phases. So we're going through a phase change. So if you had three phases, you would have three terms in each of these, right? So typically when we do this, all of the P integrals are 0 because it's done at constant pressure. So when you integrate this, you'd integrate that, integrate that, integrate that, and so on. So this one, those turn out to be 0 because we're not changing the pressure. Now, this is not true if you're working in a refrigeration cycle. You know, if you're doing a refrigeration cycle, then you've got a change in pressure, a change in temperature, and change in moles of, like, you know, how much of the gas versus the liquid you have. But for a lot of, you know, things, you're just boiling water, pressure is not changing. So, okay, so what is partial of H with respect to T? Partial of H with respect to T. It's the heat capacity. So these two partial derivatives are just the heat capacities. This is the heat capacity for substance number 1. This is the heat capacity for substance number 2. And typically we don't just deal with heat capacities, we deal with molar heat capacities. So you have to multiply by N in order to get to the absolute extensive enthalpy changes. So notice what these two terms turn into. What is this one going to turn into? Yeah, given that Cp is constant, right? You can pull it out of the integral, and then you get NCp delta T. Given that this one is constant, you pull it out of the integral, and you get NCp delta T, where this would be like phase 1, that would be phase 2. Okay, and then what about these last two terms, right? What do these account for? Counts for the moles. So this is saying that how are the number of moles changing for number 1? How are the number of moles changing for number 2? Okay. So let's kind of think about that for just a second. What is this term right here, the partial of H with respect to N? You know what that is, by any chance? It's how enthalpy changes with number of moles. Do we have a more common, like, Yeah. It's not specific heat. Specific heat is the heat capacity. But instead of per mole, it's per gram. That's the only difference. So functionally, it's the same. It's just the units are a little bit different. Yeah. So what about this? Let's just graph it up, see what it looks like. Okay. If I have 0 moles, what's the enthalpy? Zero, thank you. And if I have, I don't know, some moles here, I'm going to have this is going to be a straight line, isn't it? Like if I double the number of moles, I double the enthalpy. If I triple the number of moles, I triple the enthalpy. Yeah, so it's the slope of this, right? Which is a constant. Which is the molar enthalpy. Typically, we use the enthalpy of formation. Right? Because our reference state is elements in their standard state, right? So we just count that to be 0, and then we go from there. So we can throw this in here for each of the phases. Let's do that. Let's pull that out, and then we'll throw them in and see what happens. So I'm just pulling those last two integrals down. And let's just say, hypothetically, that this is state 1 and this is state 2. Where, like, this one right here is state 1, that's state 2. So in my integrals, what is state 1 going from? It's going from some starting value of n, right? We'll just call that n, to what? Where does it end? To 0. Because I'm going from state 1 to state 2. So state 1 goes away. It goes from whatever it started with to 0. What about state 2? What happens to it? Starts at 0. And then it ends at n. So if I go ahead and integrate this stuff, right, because my delta h's, they come out of the integral. So this is just negative delta h of formation 1 times n plus delta h of formation 2 times n. Or I can factor my n out. What is that? Yeah, it's the change. It's the delta H for, in this case, the phase transition. But this could be true for, like a chemical reaction, right? It could be delta H of the chemical reaction. It doesn't really matter. This turns out to be delta H, in this case, of vaporization. So when we go back here, I just want to point out that this is all part of one sort of giant equation in thermodynamics. But it's helpful to break it up in all these pieces. And we can do that because enthalpy is a state function. So it doesn't actually matter, how you crunch the numbers, right? As long as you start and end at the same points, you'll get to the right answer. Okay. I'm going to skip over that example. I don't think you have a... What did I put in your homework? You haven't looked at it, so you don't know.
There is a heat. I think there is a heat curve.
Oh, there is? Okay.
Not on the partial derivative one, but the second one.
The second one? So it has a heating... What does it say?
I just remembered the graph.
That is a Maxwell relation question. Yeah, not a heating curve. Okay, so you don't have a heating curve question. We'll skip over that. I doubt you're going to have to do that in your professional life, so. I haven't had to do it in my professional life. Other than teaching. I have to be able to do it for teaching purposes. Okay. All right, so, so take a look, seriously, take a look at your homework, and then we can kind of address some questions that you have on Wednesday. I mean, I've kind of gone over everything that you need to know for the partial derivatives, but it may, once you get into it, it's pretty easy to get kind of turned around and like not quite know where to go. So, yeah, attempt all of them, and then we can address any questions you have on Wednesday. All right. Okay, so we're going to review a little bit about entropy. And we've already kind of introduced this a little bit with statistical mechanics. Entropy is defined to be the reversible heat divided by the temperature, right? So this is the classically, this is the definition of enthalpy. I could put a little definition thing here. This is what enthalpy is. I'm sorry, entropy. This is what entropy is. You've probably, so the second law of thermodynamics, which is the law of entropy, says that entropy always increases. And in order to appreciate that a little bit, we're going to take a look at entropy. And we're going to break entropy up into two pieces, okay? So the entropy that is produced by the system and the entropy that is exchanged with the surroundings, okay? So the exchange comes from the heat transferred. The produced is not from heat transferred. It's just produced entropy. All right? So that's a little bit confusing because entropy is defined to be dq reversible over T, right? And so you're like, well, Q is heat transferred. So how can you produce any, quote, heat transferred? And the way this happens is the reversible, this is the reversible heat transferred. If you go through an irreversible process, then you're producing entropy. And you're no longer, I mean, you're also exchanging entropy, or you can be, but you are not, you're producing entropy when you go along an irreversible process, and you're not producing entropy when you go along a reversible process. In other words, this is greater than or equal to 0. It's 0 for a reversible process, and it's non-zero for an irreversible process. Okay? And then ds exchanged is simply dq over T. So we're going to use like the actual heat transferred for the exchanged entropy. So with this in mind, we can say that ds is greater than or equal to dq over T. Notice what's missing. There's no reversible, right? So this is equal for a reversible process, and it's greater than for an irreversible process. So this still holds to our definition of entropy. ds is dq reversible over T, which is what we would have here. ds is equal to dq reversible over T if this is a reversible. If it's not reversible, then ds is bigger than that, because ds produced is greater than or equal to 0. Okay, so this inequality is a little bit helpful, and we'll see how we can kind of make use of this in just a minute. All right, so for a constant pressure and temperature process, the first law is this inequality. Now let's just go through real quick and kind of point out everything. So du is less than or equal to TdS. Now what typically belongs here? dq. Right? So dq is what belongs here. Remember the first law looks like this? That's the first law. So what we're doing is we're taking this inequality right here, we multiply T over. So dq is less than or equal to TdS. So when I plug in TdS, I introduce this inequality. All right, and then the other thing that we're doing is putting in what dW is. dW is the expansion work. That's PDV, negative PDV. And then we're including this non-expansion work, which at this point is helpful to kind of, I mean, we need to keep track of that. Okay, because there's more than just expansion work out there. So we're going to move everything over except for the non-expansion work. And we get this. this is our resulting inequality. So if we pull out our differential operator, we get this. All of this stuff right here is G, Gibbs energy. Because remember, Gibbs energy is H minus Ts. And what is H? U plus PV, right? So this is, all that stuff is G. So then we wind up with this inequality right here. Let's interpret this. What does this mean? You guys probably remember from like general chemistry that delta G has to be negative for a spontaneous process. You remember that? So something like the decomposition of water, where delta G is positive, taking water and turning it into hydrogen and oxygen. I don't know exactly what delta G is for that, but we can look it up. So delta G is positive. So then you'd say, not spontaneous, right? Okay, then you go into the lab, and you did this at one point. You put some electrodes in there, and you decomposed water. And you measured, in GChem 2 lab, we measure the rate of that. So when you do that, is that a spontaneous process? Is there a correlation? So we can cause a non-spontaneous reaction to occur. Is that what you're saying? Yes. You okay? And vice versa. So we cannot cause a non-spontaneous reaction to go forward. If it happened, it was spontaneous. So, if we write that, let's write this out in integral form, delta G what this means is that the real criteria for spontaneity is this. Delta G has to be less than or equal to the non-expansion work done. So in the electrolysis of water, there's electrolysis work done, which changes the criterion for spontaneity. Okay, so you're right. If we didn't do that work, it wouldn't happen. But this is the inequality that must hold. 0 doesn't belong over here. The reason why we typically put 0 over here is because we want to know how much work we can get out of it, not how much work. We calculate delta G's to determine how much work we can get out of it, or how much work we got to put into it in order to make the process spontaneous. All right? So if it happened, it was spontaneous. We don't ever observe non-spontaneous processes. It just doesn't happen. That makes sense? We're out of time. I guess Liesl didn't make it.